That is basically the selectivity in the rubbery polymers is related to the difference in the condensability of the different penetrants, as we saw already. And as I was mentioning, this PDMS is one of the most interesting one, particularly for the high permeability he has for this VOC. And that we see in this separation of vapors from inert gases, nitrogen, etc. That is one of the area of particular interest. The glassy polymer, normally they have high selectivity and also quite good mechanical properties, but relatively low permeability, and that is related to the fact that the free volume that where the penetrant can diffuse is relatively small. Normally, that is the one typical number that is a certain amount of free volume, about of the order 20% is block, is fixed in the polymeric matrix during the cooling procedure, or just for the fast removal of the solvents. Is it, however, to remember that the free volume that you can form in your glassy polymer, very often they are not interconnected. So it's not 100% available for the transfer of the penetrant. Some penetrant can be blocked in, and that is one of the problem that can eventually has to be solved. And also there is on the membrane surface, the surface available for the penetration of the penetrants in the membrane matrix can be relatively small. There are some polymers, glassy, more and more under investigation, characterized by relatively high free volume, and that are the one that today are under the attention of researcher, the one already known and new one that people are discovering. In this department, as you know, people are synthesizing new polymers, just trying to have higher free volume and to avoid this, the non-interconnection between the different volumes. And some of these polymers were traditional as a polyimide or a PPO. Other ones are new in the sense you can increase the free volume, for example, through thermal treatment. And that's typical, the TR polymer that some of you are just working on in this lab. Or today, these polymers with intrinsic microporosity, which is another family of polymer quite interesting for this kind, glassy, and with a significant level of free volume. Remember that the origin of the attention and the understanding of the mechanism in this kind of material is very much being related to the one of the polymer I was mentioning before, which is the poly-3-methylsilylpropene, which is, I told you this story, initially people were assuming was a rubbery polymer, was not, is a glassy, but has a special structure. And the special structure has been, now that we understand the structure, through analysis, simulation and the modeling of the polymers, we are able to predict how to operate with some other polymers having eventually the same properties. Poly-3-methylsilylpropene is interesting, but has a one problem, that is not very stable with time. So you can prepare very interesting membranes, high selectivity combined with quite interesting permeability, but still we don't have a large scale utilization of this kind of polymer because this mechanical stability with time is not interesting enough. So you can make there is a lot of publication, a lot of interest, but not easy to realize. We were showing already what does it mean for most part of the polymer, this Robinson trade-off. If you just plot the selectivity as function of the permeability, for large part of the polymer, we have some exception, we will show these reverse selective polymers, but normally we have that increasing permeability, the selectivity is significantly decreasing. in more or less, but that is the behavior for any couple of different polymers. So that is one of the problems we have, and the Robertson plot is just confirming this kind of behavior for hundreds. Each one of these red is the addition of many different polymers. You can see here that everything apparently is following this rule. And initially in the 80s, when for the first time this kind of diagram was presented, apparently there was no polymer able to overcome this line. The situation is different. We are learning that this situation, there are polymers that can be better, giving results better than this in this area. This kind of line has been updated in the 90s and maybe will be updated again shortly. But in any case, we know that you are able to overcome these limits, but not with single polymers. You have to go to some mixed matrix, you have to add something, or we have to go to inorganic materials, etc., etc. And that is another area where people are working, or you have to induce special transformation in your polymeric material as the one that you can induce by thermal treatment on some special kind of material. As we discussed already, not only polymeric material can be utilized for making gas separation, but also we can have also, in the case of gas phase, inorganic ceramic membranes. Eventually, the mechanism will not be anymore solubility diffusivity as the one that we have been describing for most part of the polymeric membrane that we are utilizing, but you can have a Knudsen diffusion or viscous diffusion, and we saw the equation that are just controlling this selectivity in this case, which is nothing more than Gram's law, in which the smaller molecules are moving faster than the bigger molecules, and the equation is give you a ratio in the selectivity, in the permeability through the square root of the reverse of the molecular weight of the penetrance, basically. Inorganic membranes can normally be produced. We use traditional system. The sol gel technique is the most utilized, for example, in preparing zeolite membranes. Zeolite membranes are one of the area in which there is a lot of research today, because people are learning how to make relatively homogeneous distribution of crystals of zeolites on some support. And that is giving you the possibility to make some interesting inorganic membranes. As most part of this system, as you see here, are just the overall morphology is given by at least 3 different layers. You have one layer that is nothing more than a physical support to the growth of the selective layer, but on this physical support, that can be alumina or any porous material, or relatively also low cost, you have an intermediate layer, already much more well controlled in terms of porosity and mechanical properties, and on this second layer, you have at the end the real molecular sieve, the real zeolite layers, for example, or any other material, can be eventually graphene or can be fullerene or some material to which you are attributing the selective properties. And this material can be formed on the surface using different techniques, from plasma deposition to just traditional sol gel, this formation for the zeolites and other different systems. And the case of zeolites, I'd like to mention, and if you have, we will try to eventually to tell something more on this preparation, is particularly interesting because zeolites, I suppose you know what they are. They are aluminosilicosilicate in crystal form with a very regular structure. And this very regular structure is characterized by some open windows with the different solution penetrants. And these windows are very well reproduced regularly along all the structure of your crystal with the same size, the same dimension, etc. So if you have penetrance with size of 20 microns, if you have zeolites in which the external windows is 5 microns, for example, or 5 Armstrong, which is the most interesting case, the penetrant cannot penetrate for sieve effect, for just real, in this case, filtration. Now, with this kind of crystals, they have 3 Armstrong, 4 Armstrong, 7 Armstrong external windows, so very well distributed and regularly with very few defects. So that is, if you can produce this kind of material in an homogeneous film, this is an ideal membrane. Not easy to form homogeneous film. You have to avoid that the gas, instead of going through the cage of this crystal, they are going through just between eventually the matrix, the polymer in which you can fix your zeolites and the zeolite itself. So the gas will penetrate not through the windows, but through the interconnection between the interface between the polymer and the zeolite. So that is the wettability of the zeolites in a polymer matrix is one of the problems under investigation. Today, more and more, however, researchers are able to try to grow this layer of crystals of zeolites on some support in a relatively very regular structure with no defects and with no holes, and so the zeolites can operate. That's why, in case of quite interesting as the CO2, attention on zeolites are not new. 30 years ago, 40 years ago, zeolites have been already investigated, but nothing happened. Today are really again under investigation. So that is the reason. Remember, they have also good thermal and chemical stability as inorganic material, and that's why they are attracting a lot of attention. And you will find some interesting paper in the literature, review also from our side. Another family of inorganic membrane which is becoming interesting in the case of gas separation is the carbon membranes. Carbon membrane, basically, you can have some polymeric material. Today, people are preparing also some hollow fibers by cellulosic material, traditional cellulosic material or others, and by pyrolysis. You just burn this material, and at the end, you have a decarbonization at very high temperature, between 500 and 900 degrees centigrade, and the polymeric precursor, that can be also polyimide, the one that we can use also just as a dense film, you transform all this polymer in carbon. All the rest is gone. And this material have a very interesting permeability and selectivity. The trouble is normally is their fragility. So it's not easy to handle, and in some cases there is also a problem of specific fouling. That means some components, sometimes humidity itself, water, can also in vapor phase, can just be absorbed initially and decrease the interesting performance of these materials. But basically the major problem is the fragility, because eventually if there is any fouling, any interaction that will with absorption on the matrix, you can have a pretreatment, and the pretreatment can remove the origin of this fouling. But the fragility is a little bit more complicated to be eliminated. Are also interesting this material because today, in this way, you can have asymmetric structure. When you are preparing a zeolite or some other inorganic, normally you have homogeneous, just no asymmetric, which means that, as you know, all in our equation, the thickness of the membranes, increasing the thickness, you are decreasing transmembrane flux, basically. One way to solve the problem, as we discussed already in reverse osmosis in other system, is to have an asymmetric structure, where the real membranes is only a very, very thin layer, as we saw before, of the tree, of the order of with thickness of 1 microns, eventually less than 1 microns, and on porous support. That means typical asymmetric structure. with this kind of material, during carbonization, we can keep the asymmetric structure of the initial phase inversion polymeric system that we've been preparing, and that is a way to have much easier than with traditional ceramic or with zeolite, for example. And in this case, I was mentioning before, the transport is controlled basically, and particularly selectivity, by molecular sieving. And eventually also with adsorption phenomena related to the operation, the temperature at which you just operate the system. But the sieving is the most interesting aspect. We are mentioning here that today there's a lot of research in progress in this area, and in some cases you can have just interesting selectivity at a certain temperature, for example, starting from traditional cellulosic material, and for the CO2 separation. This work of this membreane in Norway, in Trondheim University, is just related to the CO2, and they've been able to have selectivity that if we can produce on large scale this kind of membrane, can give a real contribution to the solution of the problem of CO2 capture and selectivity. However, these membranes are not at the moment produced still on large scale. The other area of interest, which is in part related also to this zeolite membrane, for example, because with zeolite you can also prepare a mixed matrix where you have a polymeric structure and the zeolite embedded inside, are these membranes that we call mixed matrix membranes. In this case, basically, you have some inorganic material that can form what we call a discrete phase in these particles, which are micro or nanoparticle, and they are incorporated in a traditional continuous phase that is polymeric matrix. The problem which exists, the same I was mentioning before, is this, the wettability or the interface between these particles and the matrix in which, and the polymeric matrix. And there are people working a lot on this. Seems to be easy, it's not so easy. So sometimes you have to functionalize this matrix, this discrete phase, for example, by fluorination. If you go in the literature, we were doing something similar to entrap catalyst, this just some polyoxymetallate in some polymeric matrix to make some, not for gas separation, but for catalytic membrane. And the big trouble is how to avoid the defects at the interface between the catalyst, that you have the polyoxymetallate, and the polymeric matrix in which you are just immobilizing your catalyst. Seems to be easy, it's not, and that's why there is a lot of work in this area. In this case, the mixed matrix can be traditional zeolite I was mentioning before. That is the first one. Silica, titanium dioxide, a lot of research is in progress with titanium dioxide today. Titanium dioxide, as you know, is sensitive to the solar radiation, so can have different kind of activities. Can be an anti-fouling, can be a catalyst, can be just adsorption, very selective some adsorption. A lot of motivation for working with CO2. If you go in the literature, you'll find a big European project called NAWADEX, in which we are involved just for immobilizing titanium dioxide in ultrafiltration. That means polyether sulfone or polysulfone membranes as a pre-treatment to reverse osmosis. It is a big project in which a lot of people are involved, and they are just preparing this mixed matrix, not for gas separation, but just for taking profit of the catalytic activity of titanium dioxide that can destroy some organic present in the water that you have to send to reverse osmosis, and that can be one of the ways to minimize, to improve the performance of the traditional ultrafiltration by adding titanium dioxide. And that's enough. Or carbon nanotubes, same story, or graphene oxide, or MOFs, if anybody is synthesizing some complexing agent or some strong new adsorbent, that can be done, they can be utilized in this way. Keep in mind that all traditional ion exchange column or all traditional column of adsorption, in which a lot of material still today is utilized, are slowly disappearing when you can redesign the chemistry of the same material, which is quite effective sometimes, in a membrane configuration. So the property of the absorption, desorption, and selective permeation, etc., are just the same, nothing changed. What is changing is the engineering of the system, having an interface that is controlling the mass transfer. And I remember, is one of the basic requirements in process intensification, basically how to control transport across interface is the easiest way to minimize, to increase the efficiency of the system, to minimize all the problem of stagnation and pathways which are not effective at all in the separation, etc., compared to the big column. You just reduce the cleaning procedure, you increase lifetime of your material, etc., etc. And that's why, in some case, the same material that you already have been utilizing as a traditional column, for example, can be utilized today if you're able, as membranes, if you're able to make a membranes. The problem is to find appropriate combination of the continuous matrix, that means the polymers, and the discontinuous matrix, which is the inorganic material, normally in this case that we try to immobilize in the system. And sometimes this also is a way to increase mechanical properties. Composite material are nothing more than just the combination of something similar. When you fly today in some plane, or when you drive your car, there's a lot of polymers. But all the polymers in the car and in the plane are not just polymers, are composite material in which the polymer is combined with some carbon nanotubes or carbon fibers or the other material, just to improve mechanical properties, in this case, no selectivity, etc., but mechanical properties significantly. All the composite material, particularly in space, etc., are just interesting mixing of some polymers with some carbon fibers, basically. And that is nothing to do with the membrane performance, but mechanical performance, which, however, are quite interesting also in this kind of operation. And that is the major problem. There are Nobel Prize, people who receive Nobel Prize, which are today involved in working on this specific problem. Try to understand which are the approach for a better control of the adhesion between the polymer phase and the external, the other particle. Apparently, seems to be why so complicated? It's complicated. It's complicated because we have to avoid that in the gas separation things are going to creating defects which kill the performance expected in the system. If you are able to do this, the potential for these mixed matrix membranes on the basis of the theoretical properties of the two different phases, the polymeric one and the selectivity and permeability of the dispersed phase is quite high, because it means that you can operate in this region compared to the traditional Robinson limits in using some of the existing or the known heterogeneous material that we can utilize. We can just have situation in which it's possible to work up here. That's what the case of cross-link mixed matrix material that have been analyzed, and that should be very, very interesting for solving a lot of problems, starting from the CO2, which is one of the major problems we have to face today. So that's why people are spending a lot of attention to this kind of situation, and I told you there are some Nobel Prize specifically working today on this problem. So it's not something that is attracting the interaction or the attention of people who are quite expert. Today we are in the situation, as we discussed already, this is not an area where we have a large-scale application already going. Everything is in progress, and there is a lot of open field for all of you working in this area. However, there is a lot of, if you go in the literature, it's possible to start to try to summarize and to have some little bit of orientation in which are the general properties of this kind of materials and when running as membranes. So you can make a comparison today between ceramic membranes, polymeric membranes, and mixed matrix membrane. As you can see here, in some case, they have this, for example, the mixed matrix have quite interesting properties compared to the polymeric or to the ceramic. Ceramic membranes have a relatively low packing density, and mixed matrix can have quite a higher one. What is interesting, particularly for the mixed matrix, they can easily overcome, bypass the Robinson upper bound. So you means forget about these limits. You can, depending from the property of the material or the dispersed phase, you can overcome the trade-off, which normally is very well respected by the polymeric one. And in the case of the ceramic, you can have permeating flux or selectivity CO2 nitrogen, that's the case, which is moderate compared to the one you can have eventually with this matrix. In terms of, for example, down here, the important aspect is how to solve the problem of repairing and a long lifetime for your module. Keep in mind that ceramics that everybody is assuming are strength, etc., they are not. If there is a damage on the ceramic material, you have just to put in the garbage. There is no way you can make any repair and reuse, etc. It's much easier with the polymeric to solve the problem. If there's any defects, you can identify which fibers, which part of the tube is broken, and plug in, block it. Eventually you reduce the overall surface available, but you don't have to destroy the module. With the ceramic, if it's broken, it's broken, and there is no way that you can solve the problem. So that it is a very complicated problem, easy in the polymer, easy also with mixed matrix. And here are some other interesting effects. For example, the case in which the resistance to harsh condition in the ceramic, obviously temperature and chemical attack is quite interesting. It's much lower in polymeric and in mixed matrix. Mixed matrix, not for this dispersed phase, but for the polymeric phase in which the mixed matrix is going to be distributed. So that the same limit that you have sometime in polymeric is also present in mixed matrix as a solvent resistant, for example. Again, you can have the additive, which is normally 10, 15, 20%, can be very resistant, but the 80% of the matrix that in which this additive is distributed, it will be affected. And so you have a limited resistance to the solvent for the mixed matrix exactly as for the polymeric one, for this reason, etc., etc. So this other case is, for one point which is important, is the swelling. You see here that for polymeric membranes, very often they suffer the plasticization phenomena, CO2 typical case, or they swell in the presence of different kind of solvents, etc., which you can be better controlled in the mixed matrix normally, and very often you don't have swelling, basically, or moderate swelling, and the polymeric they have. When you go to ceramic, normally swelling is not present. Inorganic material don't swell. So there is some conclusion on the basis of what has been done until now exists, and not too much. So still a lot of work has to be done for new membranes and new materials. If you go now to look the real number that we have obtained until now for practical application, remember that there are, I said, we don't have dominant presence of membranes in gas separation as the equivalent when we are talking about reverse osmosis, etc. However, there are situations in which membranes works for gas separation. You heard already something probably in the previous lectures, but some areas are already well established. For example, when you want to separate oxygen from nitrogen, or better, nitrogen from oxygen, this is a dominant technology today. That means the nitrogen production, non-cryogenic, is only the competition with the cryogenic, in this case, is only related to the size of the plant. So the engineering of the system, which is a little bit more complicated than the engineering of the system related to the cryogenic or to the PSA, the traditional other technology, in membranes is a little bit still to go and a little bit more complicated. But in principle, the separation oxygen-nitrogen, particularly if nitrogen, the product of interest, is a dominant technology. Here you have a lot of membrane that have been studied, and you can see here that that is the kind of behavior. You can have also all these points here are material which are not traditional polymers. It's not just this polyimide, etc., but they are system where there is zeolite together with polyether sulfone or some iflon, which is a traditional new fluoropolymer with specific properties, and the Robertson plot basically is observed at the highest separation factor. The average is around 6 or 7. Most part of the data are 6, 7 between these separation factor. Few numbers, very few, can be around 10, 11, 12. And when you have this number, before trusting, you have to measure again, etc., because also in literature there is a lot of confusion, and you don't have only to check the selectivity, but the lifetime of the membrane. Sometimes, if you go in literature, you find some of these nice points, but you realize that they've been working for 1 week or 1 day or 2 weeks. Interesting for making publication, but not interesting at all for the industrial application. In few cases, however, these membranes operate particularly if you have to produce nitrogen. The conclusion is that if you want to produce oxygen using these membranes can be produced. But also if you are working in a relatively low oxygen concentration. If you want to produce pure oxygen, forget, except for medical application, which cost is not an issue. So if you go in hospital, sometimes you will see people living on systems which are membrane system. But in the hospital, the cost of the operation is not really an issue, because that's the only way to control the life and to have people surviving. But if you want, for example, to use enriched oxygen for combustion problem, or another system where cost is important, today up to between in the rate 25–40% of oxygen, you can compete with cryogenic production because relatively a small concentration, you don't need very high selectivity, and this plant normally can compete with cryogenic in terms of cost, except because cryogenic are big plant, and normally with the big plant there is no competition yet. But if you work at a relatively low level of oxygen enrichment, well, you can do something. In the other case, by the oxygen produced by cryogenic. Cryogenic, I understand, you know what does it mean. It means that first you make a liquid, and after you make distillation of the liquid phase, which there's a lot of cost, but is very well established. Distillation, you know how to do it. The other area where there is a lot of attention is separation of CO2. And there are two areas in separation of CO2. One is the CO2 from methane, biogas, and the other one CO2 for nitrogen, which is CO2 capture in post-combustion, for example, in all the in the flue gases, etc. You can see here, again, most part of the membrane that are existing are just well respecting the Robinson plot. They are just at the lower value than the one predicted. This Robinson has been updated with the new polymers. And if you want to overcome the limits, you have to go to some heterogeneous system. That means silica or some TR polymers or some other additive that you can immobilize in your polymeric matrix. These three here are just carbon, metal-loaded carbon membranes that are just in the area of the carbon system we were mentioning before. Otherwise, you just stay under the level. Here, the separation, as you can see, much higher than the one oxygen-nitrogen, is of the order of 70, 80, which are a good number. In the case of CO2 nitrogen, which is most important case today, because CO2 nitrogen means just to solve to contribute to the solution of the problem of the CO2 capture. That means global warming. So there's a lot of interest, and most part of the existing real membrane are lower than 70, 80. 35, 40 was typical number. And as soon as you want to do better, you are just have to go again to some hybrid membranes with PEBAX or PPAG with silica or some other additives. There are some in this area new data coming out. The one I was showing you before by Margaret Britt, for example, approaching 80. If you arrive to have a standard, long, stable membranes with selectivity CO2 nitrogen of the order of 80, 100, a lot of a problem of global warming can be easily solved. And that was a lot of modeling and simulation already exists in which you can show also that if you approach this factor of 80, 100, you can produce your CO2 at cost quite interesting, to the point that you can use the CO2 produced in this way from any industrial flue gases, basically, for starting what is called the C1 chemistry. That means the CO2 that you are producing in this case will be the basis. You can substitute the oil. You can interact the CO2 with hydrogen, and the CO2 plus hydrogen, you can, depending on the catalyst, you can produce acetic acid, you can produce methanol, etc. And this is C1 chemistry. So forget about oil, and you just use the CO2. So what you have to do, instead of reducing CO2, you have to increase CO2 production, but you have to separate and using CO2 as for starting this, all the other chemical that you need from CO2 plus hydrogen. The problem in this case can be the cost of the hydrogen. As you know, hydrogen does not exist, so we have to produce hydrogen. With traditional system that we are using today to produce hydrogen, maybe this kind of approach is a little bit complicated, and the Japanese that were offering this solution years ago, they are still offering this solution, but does not work. But if the amount of hydrogen produced via nuclear energy is increasing, that will be quite interesting possibility if you have membrane that work up here for a long time, etc. That means membrane with selectivity of the order of 80, 100. So that's today, most the good membranes are much lower than this, 35, 40, etc. How can we solve this problem? And something that is very familiar to you, because what we have in our system, and we discussed already, is that the transport of the small molecules, oxygen, nitrogen, hydrogen, CO2, etc., in our material, it takes place by diffusion in the free volume elements or cavities which exist in our system. These are called transient because in most parts of the system, not in zeolites, but in other cases, these cavities are moving. They are not blocked. They are not just a crystal. This is amorphous system in which this free volume can be open and closed. The same when you enter in the sea. When you look, the sea is a big, constant distribution of water. but you are entering and swimming, and you are opening in front of you and just closing on the back of you. And you have to imagine the polymer is exactly the same story. Oxygen and nitrogen will penetrate, opening the free volume, and the same free volume will close when you just move on. And so that is the situation we have, where these cavities or free volume is formed by random thermally stimulated motion of the flexible organic chain. So flexibility is a very important aspect of the morphology of our polymeric material to obtain a good permeability. In the meantime, we have to combine this flexibility with some kind of formation of rigid cavity that will be related to the selectivity of the system. So that will be the combination. And here you have, for example, in glassy material, the most selective material we have at the moment is a polyimide or polysulfone or polycarbonate. Normally they have a cavity of the order of 0.3 nanometer, or eventually lower than this number, and they have broad distribution of the cavity size if you just make an analysis. When you are going to see the most permeable, these were the most selective material. The most permeable one as the polytrimethylsilylpropene that we were mentioning before from the glassy. Again, here you have the cavity size distribution is around the same number, and 0.3 nanometer, and with the radio of between 0.6 and 0.7, basically. And they have a very good connectivity. That's what makes the difference with the other material, where there is eventually there's no interconnectivity between different cavity, and that is the origin of high permeability for the polymer. However, this only for small molecules, and the separation when you go to small molecules, as the one the oxygen nitrogen, this with a relatively low kinetic diameter, these values are not sufficient for making a good separation. And also the other problem which exists sometimes with this kind of material, the polytrimethylpropene, I told you, is not stable with time. So the large cavities, which are quite interesting at the origin of this selectivity, collapse. They destroy, and there is no way, this problem is irreversible. You cannot restore the properties. That's why this very interesting material never succeed until now, at least, to become. So how can we do? How we can overcome these, the limits existing? The way to do are two. One is by increasing stiffness of the polymer chain and simultaneously increasing interchain spacing. And that is what it can happen, for example, in polytrimethylsilylpropene, where we have this interesting branch along the polymer. Or we have to control the free volume element formation, how this free volume is formed, through spatial rearrangements of the rigid polymer chain segment in the glassy phase. These two approach, these two strategies, can be of interest for solving the problem. And following this strategy, that is the work some of you is doing or some other people are doing. For example, as you know, in this department, Professor Hobum Park and Professor Yomo Lee, etc., in the years, have been able to realize polymers with cavities turned for fast selective transfer of small molecules and ions. And they have, this material are characterized by intermediate cavity size, narrow cavity size distribution, and the shape reminiscent of bottlenecks connecting addition chambers. And the use of this is, you can find here, probably you are more familiar than me because you are working on this. You can have some kind of polymeric chain elements in which is present this benzoxazole phenylen ring or a benzithiazole phenylen ring. And this prevents large interchain, indiscriminate torsional rotation, but increase the efficiency of cavity formation and avoid what is happening in polytrimethylsilylpropene, the problem of this collapse of this structure in with time, basically, or under the operation, the condition of operation, that inhibits a rapid collapse of the cavity that you create in this way. And that is the most important part. These materials, they are stable with temperature, and basically this transformation that you can induce by thermal treatment up to 400 degrees centigrade is irreversible. Basically, you can have this final morphology, and at the end you have a well-connected, narrow side distribution, free volume elements, which are interesting for the kind of separation of interest. And that is a lot of work has been done, and this material can be just one of the new kind of material in which you don't change, there is no addition, there is no mixmatic, etc., but you are inducing what we call also a post-treatment of your polymer. Keep in mind that this approach is quite interesting and also successful, because people don't remember sometimes, but this approach has been already utilized also in reverse osmosis. The first traditional reverse osmosis membrane in cellular acetate, if you go in the literature of the 70s, you will see that when you prepare cellular acetate by diacetate, triacetate, etc., after casting your membranes at room temperature, you always make a thermal treatment. We call thermal annealing. And this thermal treatment is changing in irreversible way the selectivity and permeability of traditional RO membranes. Not the same problem, because cellular acetate is not this kind of polymer, but the post-treatment is been always something that you have to try. And the cellular acetate you can change significantly. You have to membrane produced at 20, 30 degrees centigrade have relatively very low selectivity. If you treat these membranes at 90 degree, and they were calling CA90, people say, what does it mean CA90? It's not nothing changing in the polymer. It's the temperature at which the membranes have been treated after preparation to increase the selectivity to 90%. You have to go back 30 years ago, 40 years ago, and you can find in the literature this typical plot for CA. Something very similar, different temperature, different polymer, 450, but you can have the same kind of situation. A total different approach, as we were showing before, is the one that you can have today with these polymers with intrinsic microporosity. In previous case, we are inducing microporosity by thermal treatment of our polymers at very high temperature, and only few polymers can have this transformation if these thiazole groups are present or not. The situation here is different. You have a family of polymers where all rotational freedom is removed from the polymer backbone, but which has a randomly contorted molecular structure. So they don't have any possibility to rotational freedom and to destroy some of these center of the rotation, but there are no single bonds in the backbone in which rotation can occur, but at intervals along the chain that characterizing this polymer, you have this spirocenter. Spirocenter means a single tetrahedral carbon atom shared by two rings. And the spirocenter is introducing some complicated morphology in your final polymer that is basically an inflexible but contoured polymer molecule. This kind of structure, during the film formation, is inducing a sufficient free volume trapped in the solid state, more than 20% I was mentioning before, basically, and which is acting basically as a microporous material containing pore of effective less than 2 nanometer, and they are amorphous and remain glassy at temperature up to 350 degrees, etc., etc. So very different approach for having this level of permeability and selectivity, but at the end of the story, same kind of situation. We are inducing a free volume, block, stable, significant number in two different family of material. this microporous intrinsic porosity or induce microporosity by annealing, by thermal annealing. Both these membranes are becoming quite interesting for gas separation, and if you are going to see this kind of data obtained today, they are basically overcoming quite easily all the limits of the upper bond of the Robinson for the CO2 methane that we were mentioning is one of the important area that you can see 9 to 19 is the number here are all TR polymers prepared at 450 degree from homopolymers and copolymers containing thermally convertible segment units. So this most of this work is basically done here in Hanyang University, and all these material are quite promising. Poly-3-methylsilylpropene is still down here, which is still an interesting material because you can see in terms of permeability is still the highest one we have. And selectivity is low, but if this material is going to be, somebody is able to stabilize the material to avoid the collapse of this nice structure, and that's, we have to find some additive to include that will avoid, this material can be still interesting because it's a good compromise, it's very high permeability, which sometimes is quite important, and you know, if you want to increase the performance of your plant, you need to increase permeability or you need to increase membrane surface. These membranes can be expensive. So the way of having this high permeability is quite interesting. With selectivity, you can, if in one stage you make 2 or 3 steps, you can solve the problem eventually. And when you do this cost analysis, having this polymer running should be still quite interesting. However, far away from the one we have at the moment. So still, if you're able, somebody is able to reproduce this kind of polymer that we know now very well in terms of morphology, etc., but able to stabilize and to avoid the collapse of the cavities, that can be still an area of research, and in fact people are working on this. Keep in mind that the nice polymer up here are all polymer with carbon molecular sieve membranes or you know, the TR polymer with some additive, and etc., etc. If you want to see the numbers, just these numbers basically are the same numbers that were reported in the plots, but you see that the separation CO2 nitrogen, which is the one very important, you know, all around the world today, in Korea, but if you go in Japan, if you come to Europe, and now if you go to China, there are big projects sponsored by the government trying to have material with good CO2 nitrogen selectivity, because that will be the way to control global warming, and today means more than this, is the way to pay less tax on your emission, because today by international agreement, if you just produce more CO2 to a certain level, you have to pay. So it's real money. So having membrane that can overcome the problem is a way to don't pay tax. So everybody, when in front of money, is trying to find a solution. And but these numbers, you know, I've told you that if you really want to do something good, you have to approach 80, 100, 75, etc. Otherwise, the engineering is too complicated. You can make more than one step, etc., but the system is still too expensive. And if you're looking here, this number basically don't exist except some strange case that nobody trusts, etc. And all the number, the only one approaching is this sieving selective carbon I was also showing before, that is this 60, which is quite decent number. Or you have to go to some other one that is this PMEEP, or 80 was 80 somewhere. Here they are. And these are again PEBAX and silica, basically, this mixed matrix material, which are some interesting ones. But the most one are just much lower than this. And when you have in some case, interesting value, keep in mind that you need also high permeability. Otherwise, you need a lot of membrane that is killing you in the process. And normally, following the Robertson plot, if there is good selectivity, is combined with bad permeability and vice versa. So we are far away for having to solve the problem. There are some strange membranes, some strange polymers that violate completely Robinson plot, so they don't follow the Robinson plot at all, and they are not very much traditional in your study, and which are what is called reverse selective membranes, system in which the big penetrants are moving faster than the small penetrants. And so that's what normally you don't expect. And that is related to the fact that in general you can prepare this kind of material where this high free volume, very big, with big cavities basically, in which the more soluble macromolecules, hydrocarbons basically, can permeate much more easily than just the small one, the hydrogen, etc. And this can be done normally by, again, realizing a kind of a mixed matrix system. You have to add some components in the system, and there are people that are also familiar to you because they have been also working at Anyang doing this kind of work. This basically, what you can do is to add non-porous particles and this nano spacer in a matrix of high glassy temperature polymers that you can improve the selectivity of order of magnitude, 240 in some good case. And that is a function also of the percent of this nanoparticle that you can add to the system. And what is happening here, that you control the disruption of the rigid packing of the polymer chain. And a typical case is this fumed silica non-porous nanoparticle in polymethyl pentene that increases free volume in the polymer matrix without this promoting the weak selective or non-selective free phase mechanism, this Knudsen or Poiseuille. Typical data here are, by the way, as I was mentioning, no Robinson, and here are some of the data. You can see that the normal butane increasing, if you increase the percent of the particles, that means increasing the normal butane permeability, and that is changing this butane methane selectivity of the glassy PMP. That is a system that was 98% of methane and 2% of butane. This is very unusual situation, and this related to this capability to entrap these nanoparticles, creating this disruption of the chain, and permeability and selectivity in both cases. Both of them can change in interesting case. Not too much is present of this one at the real industrial scale, because also these membranes are not easy to reproduce and to control their performance, but it's quite interesting curiosity, and more people in the future maybe will pay attention. What is quite interesting, and you have to learn a little bit, not too much, but a little bit in gas separation, is that the engineering of gas separation is much more complicated than engineering of reverse osmosis and ultrafiltration, etc., etc. There is much more to be done in the design of your system than we have been discussing in RO. In RO, if you remember, we just say that basically you have 2 or 3 different kind of configuration in your module. If instead of one single, by the way, you will never use membranes, you always have a module. Module means the assembling of your flash sheet or tubular or capillary, etc. The membranes, normally you don't handle membranes, you need the module. In reverse osmosis, when you want to handle the system, you can have in parallel, in series, depending from the overall capacity of the plant, but what you have to be able to do is to reproduce for 30,000 modules sometimes. Each one of them is supposed to have the same performance of the single one. That means the pressure at the entrance and the pressure at the exit, the pressure drops along the module, the cross-flow velocity on the membrane surface are supposed to be the same. So you have to make a good analysis of the pressure drop along the system, of the overall power of your pump to have this kind of performance. All the modules, at the best, are supposed to operate with the same basic parameters in terms of pressure drop along the module, difference in hydrostatic pressure on the membrane surface, and cross-flow velocity, such a way to control concentration, polarization, etc. When you start to talk about this gas separation, the engineering is a little bit more complicated, and I will just mention some of the problems. You will hear about the cascade column system, cascade and column together, etc., etc. And the optimization of the plant is very much related to the capability to design this assembling of your module in appropriate way. A little bit more complicated than what we have been discussing in RO. First of all, the basic design of your membranes are the same than we had in this liquid phase, and you can have membranes which are flat sheet, you can have hollow fibers, capillary, or tubular membranes. Some of them with the same material. So the motivation for having flat sheet or tubular has to be very clear in your mind. People are not doing this because they like a different design. They are doing because when you operate, you can have different performance depending from the geometry of your system, particularly in terms of energy consumption, in fouling problem, the interface, etc., etc. So going from flat sheet, for example, to hollow fibers, there's a big difference, but you have to understand why. Just to anticipate, contrary to what we have been discussing in a liquid phase, most part of the membrane that people are using today, industrial level, are hollow fibers in gas separation. And the reason was that initially the idea is that the same problem that are creating troubles in reverse osmosis or in liquid operation are less severe in gas. Gas are much easier to clean, to pre-treat the gas stream. If there is some particle, etc., there are already systems in which you can easily reduce the percent of contaminants, particles present in the gas, and the number of other chemicals which are present is normally much minor than the one you can have in a liquid system. In air, the prevalent component is nitrogen and oxygen. The other one, they are 80%, 20%. The other one are 1%, 0.1, etc. Very different situation can be sometime in liquid phase. So people were assuming, and they were right, that in hollow fiber is the most interesting configuration for gas separation, because you don't have a problem basically of plugging entering the module, which was the problem in reverse osmosis. Remember that when the reverse osmosis started, after the initial first experiment using flat sheet or tubular, immediately people were trying to produce hollow fibers. DuPont went to the market time ago in the 80s with a big investment producing the most well-known and effective RO module, which is hollow fibers. And they spent a lot of money. There were not just students or professors taking decisions. It was all DuPont. At one point, they had to cancel and block the investment and remove, because hollow fiber were not running appropriate way. So they've been learning time by time that there was a fouling problem not easy to be solved. Only one company today is still working in desalination with hollow fiber, and it's Toyobo, Japanese. They still are working with the traditional celluloacetate membranes in hollow fiber configuration, basically in Middle East, where there are some other motivation. Today, maybe some of you will start to work again with hollow fibers in desalination, because with all the new pretreatment we have been introducing in RO, that means nanofiltration, MBR, ultrafiltration, and not the traditional pretreatment of that time, maybe that also desalination will look again to hollow fibers. But at the moment, you will find in every 100 plant, 1 or 2 are hollow fiber. All the other ones are just in liquid phase, just spiral wound or eventually tubular in some few cases. In gas, just the opposite. In gas, hollow fibers with this level of geometry. That means, with this the outer diameter from 0.08 to 0.8 millimeter, internal diameter 0.04. That means about 20 microns, 60 microns, 20 inside, 60, 40 outside, etc. are traditional, and most part of the membranes per large plant are all hollow fibers, very different than the other case. And you know what does it mean. That is a typical module that you will find. Here there are 1,000 and 1,000. That means single module, the small one, in a bundle of this industrial system, you have a 1,000 square meter of membrane surface using hollow fibers. If you want to have 1,000 square meter of membranes in flat sheet, also if you are making a spiral wound, still you are filling up this room. With this one, you fill up just 1,000 of this room. So this kind of assembling is quite interesting. Normally they operate in counter current. Counter current, as you know, is much more effective for controlling this along the length, the driving force in the system instead of co-current. So normally that is you have 1,000 and 1,000 of these fibers, and you can operate in two different ways here, because you can operate in, that's already the first difference that does not exist in RO. We can operate here with having the gas penetrating inside the fibers, or the one penetrating outside the fibers. So you can have the feed that just enter here and is entering in all the fibers one by one. That's the same configuration that normally we have in ultrafiltration in reverse osmosis. But in this gas phase, you can also have the feed which penetrate from the external of the fiber, and that means the retentate will accumulate outside the fibers, and the permeate is going inside and will come out from here. Just the opposite than happen in the other case. And there are few cases in liquid. In some liquid case, you also can operate in this way, but this difference is much more significant in gas separation. So that's the first difference. This typical example of a big elements. Also here, one time the elements were this one, and now are this one. This is this one, but this, if you go the reference here, I think is, I don't know, but is old, because this one here you can find 10 times bigger. Same problem that you have in reverse osmosis. So remember today, one of the ways to reduce the cost of the final production of water or of gas here is the size of the module. And when you are confident about your membranes, etc., you can, there is no reason that you can have this module huge. In RO, it's already existing. In RO, today there are modules, initially at my time were 4-inch. There's the diameter and 80 centimeter length. Today, the module are 36 in diameter and 3 meters high. And that means people, they are very confident of the technology, on the membrane quality, etc. There is no problem, because single module, if you destroy a single module of this size, it's a lot of money. If you destroy 4-inch, it's a few $100s, but when you destroy one of the big ones, it's much more complicated. Gas is following the same, so also these ones are changing. Advantages, disadvantages of the hollow fiber, assume that most part, everybody here working, except when you do the first testing in the lab, as soon as you start to approach some interesting results for gas separation, you start to spin fibers, so you don't make any more flat sheet. And when you start to make fibers, the advantage is very high packing density. That means surface area is very high compared to the volume, and very much more cheaper in production, in handling, etc. The drawbacks is that there is a relatively low resistance to the pressure. If you have to work to high pressure, that is higher than if you work, for example, it depends in this case if you're working with feed outside or feed inside. If you work feed inside, you cannot overcome with these fibers of the 40 microns, 50 microns, don't overcome 20, 25 atmosphere. That's with the normal material you blow on, you just destroy everything. You can change this performance having a hybrid system. If you add something to your polymer, mechanical strength is increasing. But normally this is the problem. So lower pressure resistance of the fibers. In the other material, when you have a support, the real mechanical resistance and resistance to the pressure is not the polymer, is the support. The polymer is nothing. So when you have a spiral wound or you have a plate and frame module, the resistance can be 100 atmosphere. If you want, you make sinterized stainless steel or nickel, can work at 100 atmosphere. Not for all fibers. They are self-resistant, and you can calculate easily for each material which is the highest pressure of collapse or blowing up, and that both of them are available. Spiral wound is another configuration, and there are also some situations with spiral wound modules also in gas separation, and we already discussed it a bit. And normally when you have spiral, if you can make big module, or the other way of doing it, that when you go to see any plants, that's true also for reverse osmosis, but also for gas, this single module don't operate as a single one except in your lab. Normally you have a nice long vessel, long tube, in which you just include your module. Normally there are 3, 5, 7, depending from the progress done. Today, easily 5 of these modules are normally present. The module there are about this 8-inch module, multiply per 3, that means 100 square meters of membranes, few hundred square meter membranes, also in flat sheet, can be present in single module. And if you multiply this module for hundreds, as normal in the plant today, that will be a lot of it. The current spiral wound contain normally 1-2 meter and up to 40 meters of membrane area, single module. Also here, when you are working on this, the drawbacks is problem in cleaning sometimes, because all this membrane rolled with the tube, you can flush through, etc. With this single module, a little bit more complicated, and back flushing is not easy in this case. Advantages are cost, relatively high packing density, less than the fibers, and easy to control this interfacial phenomena, because in this module there is a spacer between the membranes. You have a spacer in between, and changing the geometry, thickness, and also the geometry of the spacer, you can control, you can induce turbulence, you can control the interfacial phenomena, basically. So this is something that is interesting. Plate and frame, very few application today, except a small one, is the easy one, the initial one that everybody is doing in the lab. And also here you have normally a spacers, and that is the clear evidence, and the control of the thickness and of the roughness, on the geometry of the space is very important to understand the interfacial phenomena, the concentration, polarization, etc., that we learned already is important as the quality of your membranes. Some of you were not attending the previous course, but in we were saying 100 times that be careful. You can have incredible good membranes, but they will never work if you don't know how to control the interfacial phenomena. And that is nothing to do with membranes, it's to do with for example, the geometry of the spacers, the roughness of the spacer, etc., etc. And that is true in any case. Gas and liquid is the same story. In this plate and frame, there is sometimes a lot of sealing, and the pressure drop can be significant, and relatively the lowest packing density compared to the other configuration. On the other side, it's very easy to change membranes. You open, put new membranes. You don't have to put in the garbage the old module. You can change easily the single membranes, by the way. You open the module, you extract the membranes, you put a new one inside if necessary, etc. And there is also the fouling, blocking the channels is not very easy. How we operate this system now? let's start to tell these are the problems. And I was mentioning that we will just mention something, but as soon as you start to have good membranes, start to learn how to operate these membranes. Because sometimes with the existing membranes, and today it's becoming more and more true and important, instead of trying to solve the problem discussing on these polymers as we were doing before, telling that instead of 60 I need 75, and for arriving 75 you start to invent new polymers, new materials, new additives, etc. Sometimes, not always, sometimes you can have the same performance, not change the membranes, but with the existing membranes, which are much better engineering. That means using the existing membranes with 60 in terms of separation factor, with 200 in terms of barriers in permeability, etc., but not just single module, etc., but looking to the way to operate. And today there is evidence of a lot of efforts in this direction. In any cases to be done for huge plant, but much more than expected also on a smaller plant, in gas, not in liquid. Here is the case. First of all, we already tell we can work in a single module at least as in liquid phase, exactly the same, in three different ways when you are looking to single module. Here is a dead flow. You can just have your permeate, you have your feed, and you just pressurize normally to the membrane surface, and you have the permeate going across and the concentrate moving out. That's exactly what we had in ultrafiltration, microfiltration. You can have the same system in which you can now, on the permeate side, you can also have your fluid, your permeate, moving cross flow on the membrane surface. And that you can go in co-current and counter-current if you want to keep control of the driving force along the length of your module. So you can have a system which you have your feed, that is high pressure, and this will be concentrate and you can remove out, but something is going through the membranes, that will be the permeate, and it will go in the low pressure phase. And the low pressure can move in counter current with the feed solution. You can have exactly the same, but the low pressure is moving co-current. And that's changed a lot. Normally, the most part of the case, we are working counter current, because working counter current is much easier to keep the same driving force across the membranes along all the system. When you are working co-current, changing the concentration, etc., and changing the pressure drop along the module, you are changing also the driving force. So the system is a little bit more complicated to predict and to analyze. But depending from the case, both configurations can be of interest. That's for starting. Now, there is another thing that you can do. And these are two different kinds of configuration. The system in which there is a reflux or no reflux of the retentate or of the permeate. What does it mean? In one case, you can use just working cascade. In the other case, you can use with the system not cascade. Here, that's module number one. I told you normally, except in your lab, all the system, real system, there is not a single module. Today, in some cases, there are 30,000 modules, single plant. Incredible big number. And that's true for liquid, but also for gas. So that you have a 1, 2, 3, 4 in this case. So starting from number one, you can have the permeate of number one is becoming the concentrate of number two. And the permeate of number two is becoming the concentrate of number three. So you're just working in cascade, one after the other. The other case is different here because what you can see here that you have that the permeate, or in this case, all at the end, all the retentate are mixed together. So at the end of the system, you will have a retentate where we've been mixing the retentate for number one, number two, number three, number four, all the retentate, and the permeate, which is the permeate coming from number one up to number four. The other way of doing is the second one, where you have the first module, and you have now that the retentate of number one is becoming the feed of number two, not the permeate, the retentate. And so at the end of the story, 1, 2, 3, 4, you will have a retentate, that is the one that is coming across the 4 modules, and all the permeate from number 1, number 2, number 3 that you mix together. The two differences are quite important because that's a different way to increase the concentration of some component in the permeate or in the concentrate. And that makes a lot of difference at the end.
Isn't that number B, isn't that basically the same thing as long membrane? So
well, at this moment, the length of the membranes is not, the membranes are the same length.
Right, so the retentate from the first membrane goes into the second membrane, right? So that same thing as having long membrane, right? Membrane module twice as long will have the same effect.
Not really.
The retentate from the...
If you mean if you have a single module, the single module independently from the, for sure that you can have different performance depending from the length of the module, but the different performance is here. So if this module is very, very long, there is significant difference between working counter-current or co-current. Because if you're working in co-current, at the end, increasing the length of the module, at the end, you can enter with 10 atmosphere, and so you have a driving force 10 against 1, but along the module, pressure drop is increasing, and at the end of the 50, if it's 1 meter, you enter with 10, you go out with 9.5. But if you have 100 meters, you enter with 10, and you go out with 0.1. So there is no driving force. Eventually, in some cases, what is happening along the module, if there is any osmotic phenomena, or you have the gas coming from the other side along the module. So the length of the module is becoming very, very important, working for single module. But in this case here, the length is not, this will be true for each module, but there is no difference. Here, what you have for each module is that you will have a certain concentrate, and this concentrate you are sending to the second module to be permeated. And the next concentrate you are sending to the next one to be permeated. So the length is an important factor for sure, but as before, for each module you have to take care of the length. By the way, what you said is also very important in many other applications. For example, more important in membrane distillation. We have PhD students working today only on optimizing temperature polarization phenomena in membrane distillation module to understand the effect of the length on the temperature polarization brackets. So that's another problem which exists in the setup, but not in this case. In this case, in principle, the problem exists, but when you compare each one, the length of here with the length of another one, but not between the two configurations. Between the two configurations, the only difference is that that here, if you are working in counter-current or co-current, it makes a big difference in terms of length. Okay? Anyway, so that's it, just to tell that in the first arrangement, there is no reflux of the retentate, basically. And in the simple arrangement, the permeate from stage 1 becomes the feed for the next tag, and the retentate is disposed of. The second case, the retentate from stage N became the feed for the next one, N plus 1, and the permeate is disposed of. All permeate streams must be recompressed before entering in the next stage. And that means energy consumption. This is important because you can have increasing of recovery rates are obtained in cascade with the reflux of the retentate or permeate. Each one of these is a way to change the concentration of the permeate or of the retentate, depending what you are more interested in the system, and you can change the kind of configuration. Okay? And that is one. What is interesting now, that if you are smart and you want to solve the problem, you can also try to combine the two. And so you have and this is a way to approach very much the traditional distillation column. If there is anybody expert in distillation, that's what distillation means, traditional distillation, cryogenic distillation, etc. The combination is that you can put together the two cascades, and you have a stripping section, that means enrichment of the retentate, and an enrichment section, actually enrichment of the permeate. in one part and the other, putting the two together to decide which one of the final configuration is the most interesting is very much related to a complicated, sophisticated, elegant study of this kind of situation, which is not obvious, and what you're looking for. Because depending from the fact that you want to enrich in retentate or enrich in permeate, etc., you can decide to have or not have, for example, this kind of cascade in this kind of column. That is one of the columns. This department has been involved in this because one time a Korean professor, Professor Wang, has been just working and developing this cascade column system, and though you can produce highly enriched products both in the permeate and retentate without pressurizing the permeate before going to the next stage of the cascade, and that means saving some energy, etc., etc. So keep in mind that when you are talking about RO, you have never seen this kind of things. It's not necessary, basically. But in gas separation, these things are becoming quite important, and you have, depending from membrane properties, module design, and what you have to obtain at the end, the overall cost, these things are becoming important. Keep in mind that in gas separation, the system is never small. It's all big, huge system, and that's why this kind of analysis is becoming one of the analyses important. Anyway, we will continue next week. Next week. And here just some examples that are showing this. Okay, just to anticipate one thing, just because I don't know if I have here. Anyway, we will continue on next Wednesday.